Okay, start one. Hello, everyone, and welcome to today's webinar, The Evolving Landscape of Water, Oil, and Stain Repellents, brought to you by the Advanced Textiles Products Division. ATP represents the safety, medical, and interactive textile product marketplace and provides a forum to exchange information, solve common problems, and develop mutually beneficial relationships. You will have the opportunity to submit text questions to today's presenter by typing them into the questions box of the control panel. You may send in your questions at any time during the presentation. I will collect these and they will be addressed during the Q&A session at the end of the webinar. The PDF of today's presentation is currently available for download under the Handouts tab of your control panel. A link to download this and the recording of the webinar will also be emailed to you later in the week. I would now like to introduce today's presenter, Frank Kewen. Frank is the Senior Technology Manager at Bulger O'Hearn, Inc., and leads development of high-performance fabric effects, including DWRs. Frank has over 30 years of experience in applied polymer chemistry, materials science, and textile finishing. Please welcome Frank.
Good morning. Thank you very much, Janelle, for the introduction. And I would like to also thank IFAI for giving us a forum today to talk to you about today's topic, water, oil, and stain repellents, and new developments in this industry. Bulger O'Hearn is a specialty chemical producer specializing in textile effects and textile enhancement solutions. We've been in business for almost 50 years, celebrating our anniversary next year. It's a third-generation family-run business, and we offer a very highly personalized service to our customers. We create and advocate for environmentally preferable and sustainable products to use in textile processing, and we are a Blue Sign system partner. So today's webinar, I'm going to basically be looking at water repellents for the most part, and really liquid repellents. We'll start with a description of what repellents are, what they do, what they're composed of, and then talk about some properties, how they're measured, and new developments in the higher performance storm-proof finishes. So basically, the definition of a water repellent finish is a chemical treatment that's applied at the fiber level and makes the textile resistant, but not necessarily impervious to water penetration, or if it's an oil repellent, to oil penetration. Being a finish, it should not be visible on the surface of the treated textile or alter its physical properties significantly. Again, it's applied to the fibers themselves and not across the fibers. Some other terms that it'll be using include hydrophobicity and hydrophilicity. It's very important in the repellent game. Also talk a little bit about why things wet and why they don't, and the surface tension of liquids, which basically governs how things will wet other surfaces, and then how you measure that, a contact angle measurement being how you look at, one way to look at how liquids will wet surfaces. So some of the terms in repellency that are important, hydrophobicity, this generally means water fearing or water repelling. Hydrophilicity is the opposite of that. That means water loving, or the ability to wet out with water. A lot of the properties of liquids as they interact with surfaces come back to their surface tension. And the surface tension is the tension on the surface of a liquid that's caused by the attraction of the particles within the liquid from the bulk of the liquid itself. So the attractiveness of the individual molecules in the liquid will bring about the surface tension. The way that liquids will interact with a solid surface is typically measured by, for planar surfaces anyway, using the contact angle measurement. And that is basically the angle that's formed with the edge of a droplet on a solid planar surface. And this will determine how well that particular liquid would wet that particular surface. And a lot of this has to do with the surface energy characteristics, both of the wetting liquid and of the surface itself. The surface contact angle can be 0, when that means that the liquid completely wets out or flows over that particular surface. At the other end of the spectrum to the right shows not wetting at all, and so the liquid remains as a spherical, droplet on the surface without any wetting. The contact angle at the very end, the highest you can get really is about 150 degrees, and that means it's completely not wetting. That's called a super hydrophobic surface if water is the wetting liquid. To get good repellency against water, you need a surface that's highly hydrophobic or really doesn't like water at all. For oils, the surface needs to be lower in energy than the cohesive forces that keep that oil together as a liquid. So it's different than what you would have with water. Water needs to have a surface that's more polar or more energetic than the water is itself. In water repellency, you're always trying to overcome or to get water to wet something, you have to overcome some very strong intermolecular bonding of the water molecules. And to the right is an illustration of how water will associate with itself through hydrogen bonding. And these are fairly strong bonds. They're easily broken and rearranged, but they are strong compared to what keeps most liquids together. For non-polar materials like an oil or organic compound, the forces that hold them together are much less. So a hydrophobic surface, one that lacks polarity and surface energy, will inhibit water's ability to wet that, which is, for repellent is what you want. So you're always trying to create with your finish a surface that is very low in energy. And otherwise, water molecules, what you want is them to remain bonded really to themselves and not to your surface. So again, you want to create a surface with low surface energy and low polarity to repel water. Some of the chemicals that are used in finishes to give particularly water repellency, the oldest types of technology were the hydrocarbon waxes and derivatives of waxes. These will give very good initial water repellency and some stain repellency as long as the stain is mostly water-based, but they do not give an oil repellency at all. They really absorb oils. Another fairly old technology are the silicones. Silicones are basically rubbery materials, and they will coat the fiber and give a high degree of water repellency, but again, they don't give any oil repellency, and the silicones tend to be a more expensive type of finish than your basic hydrocarbon wax types. The newest and most effective repellents are based on fluoropolymers. These are compounds that will coat the fiber, like the other types, and give a very low surface energy fluoropolymer. The fluoropolymers tend to have the lowest surface energy of really any type of material, and they will give both high repellency to water and oils, and really are the only type of finish that's available, a type of polymer available that will do that. I'm going to show some of the, being a chemist by nature, I would like to show some of the molecules or examples of molecules, kind of a generalized version of some of the things that are used in finishes for repellency. This is an acrylic-based material on the left, and on the right is your basic hydrocarbon wax type material, where the X gives is like 10 to 24 of those repeat units. And the CH3s and CH2 groups are very good water repellents. They have very low surface energy, or they'll produce surfaces with low surface energy. They're not particularly durable, and they're not particularly easy to put on with water. They're often combined with chemicals or polymers on the left, where you have an acrylic backbone, and side groups, where the side groups could be these long chain alkyl groups, which give the hydrophobicity and the repellency. They also have groups like free acids, and they could also have a hydroxyl, and these are used to actually bond amongst themselves with other additives in the mix, or to groups on the fiber surfaces themselves to give durability. Also, they're frequently derivatized with what's on the left side, and that is a quaternary ammonium compound, or a quaternary ammonium group. And these are used to give stability to the aqueous dispersions, which these are delivered from. And also, they're used to help absorb the finish onto the surface of the fibers. The fibers typically have a slightly negative charge, and if you use a repellent with a slightly positive charge, you'll get very good coating and uniform coating onto the fibers themselves. Silicones have this generalized structure. The silicones used in treating fabrics have this generalized structure. At the ends are unreactive silicon groups that are bonded with methyl groups, and these are very, very low in surface energy, produce very, very low in surface energy. And the main part of them in the parentheses to the right with the subscript D, these groups also produce very, very high levels of repellency to water. The other groups, the SiH with a methyl group in the parentheses to the subscript N, that is used as the means to cross-link these molecules or these polymers or prepolymers onto the surface of the fabric or the fibers. And they'll usually react with a catalyst, and when they dry and are cured in an oven, they will cross-link through that SiH group with themselves, and then also can react with groups on the surface of the fibers themselves to give some durability. Fluororepellents can be very complex in their structure. This is, again, a generalized chemical structure, and the two repeat unit groups on the left are basically the acrylic backbone, and the types of groups that you have in there are used to sort of tune the properties, the mechanical properties of the acrylic as far as its softness and again, sometimes its durability as well. On the far right with the subgroup C is, again, the quaternary ammonium functionality, and again, that's used to keep the dispersion stable, when you're storing it or when you're making it, and also to help in absorbing the finish onto the fibers via the ionic interaction. They can also, I didn't show it here, but there could also be some groups that might have a free hydroxyl group, or maybe a free derivative of an aldehyde that can be used to cross-link the system and also to bond it to the fibers. Really, the most important group on here is the one with the subscript F, the right, and this is the fluoroalkyl or perfluoroalkyl side chain. This is what gives this polymer its ability to be a high repellent for water and oils. The N group on the CF2 is, in this case, is 5, so this is like a C6 based or short chain fluoroalkyl hydrocarbon, which are used quite a bit industrially for repellency. And these groups, the CF2 and the CF3 especially, give an extremely low surface energy. These groups, along with the alkyl groups I showed in some of the earlier slides for the other types of repellents, they have the ability to migrate themselves or orient themselves to the very surface, to the air surface on the outside of the fabric or the fibers once they've been applied. And this is very important because that's where you want them to interact with water or oil to repel them. You want them to organize themselves and act like almost little tiny hairs that stick out, little molecular hairs that will stick out and bring about the low surface energy and repellency. These types of repellents are typically applied in a mill setting where in a semi-continuous process, roll to roll, the fabric that's ready for finishing is cleaned and ready for finishing, gets dipped into a bath made up with water and the concentrate of the DWR finish. It goes through there, wets the fabric out. The fabric then goes through rollers where it's squeezed to give a nice uniform penetration of the material and squeeze out excess. And then it goes into an oven to dry and cure the finish onto the fabric. So again, this is a semi-continuous process, and it completely treats both sides of the fabric. Also, the DWR could be foamed with air, and this foam applied to one side or it could go to both sides of the fabric in a semi-continuous way. In this case, you save some energy because you don't have to remove as much water as the other methods, and it does allow you to apply the DWR on one side of the fabric if you want. Another way to do that is to use just a regular bath like the first type, the dip squeeze method, and instead of dipping the fabric in, you apply the DWR bath to a roll, and the roll applies it to one side or maybe two rolls to both sides of the fabric. So that again gives you some flexibility in where you put the DWR. Another method, which is really often used for garments or sometimes with knits, is a batch process called the exhaust method, in which your DWR is dissolved in a vat of material, and then the garment or the fabric is put in there, and then the DWR will attach itself to the fibers. It's then brought out, dried, and cured. And again, that's more of a batch process, but it can be used to actually treat garments as opposed to just linear fabric. So the performance of repellents, particularly water repellents, are tested by a number of standard tests, most of these through the AATCC group. The most common one used by most people in most mills is the spray test, the test method 22. This uses a small volume of water, about 250 mils, short duration, and about a 6-inch drop height onto fabric that's stretched over a ring. And again, it gives an idea of how the surface of the fabric will repel water in a fairly gentle spray. And there's a rating system that's used from 0 to 100. So it's a qualitative type of repellency rating, 100 being the highest, 0 being the lowest. You can make the system more a little more aggressive by using the test method 42, where more water is dropped from a higher point. This is from 24 inches, and in this case, you would have on the back of the specimen, there'd be a blotter that's pre-weighed before the test and then weighed after to see how much water penetrates through and wets that. So you get both you can get a qualitative and a quantitative measure of the repellency. There's also the rain test method 25, and this uses a spray. It's more on a horizontal spray, 12 inches away. It can go from 2 to 5 minutes in duration. Again, there's a witness blotter on the back of the specimen to measure how much water actually passes through and wets that. So you get both, again, a qualitative measurement and a quantitative measurement from that. A much more aggressive method for looking at water repellents is the Bundesman method. And this is basically a rainstorm simulation. I'll show in a minute how this actually works. And it's a 5-foot drop with, up to many gallons of water being applied in like a simulated rain manner. And again, this will measure. You can measure the repellency of this. You can weigh the fabric beforehand and then after to see how much water it absorbs. And then since it's instead of just a ring, it's stretched over a cup. The samples are stretched over cups, and you can measure the volume of water that passes through. Now, one of the types of a new type of repellency that is available is called storm-proof breathable finishes. And this is a type of repellency you can really only measure with something like the Bundesman, where it gives an outstanding degree of, sorry, I think I skipped one. So I'm just going back, there's a couple more methods that are frequently used before I get to the Bundesman, and that's dynamic absorption, where samples, treated samples are tumbled in a water-filled jar, and their absorption is measured quantitatively. Aqueous liquid repellency, this is a drop test. It's very easy to do, and it's used in a lot of mill settings where you have different wettable fluids based on different ratios of water and isopropyl alcohol. Again, the higher level will give, I think it goes up to about 8, is the highest level of repellency. Oil repellency is done very similar to the drop test of the liquid repellency, and this uses different types of hydrocarbons. The lowest one, the easiest one to pass is like a motor oil or mineral oil, and it goes all the way up to almost something like gasoline, which is very difficult to keep from wetting your surface. And so you get a number for that. There's also the hydrostatic pressure test method 127, and this is used to measure the penetration of water under a high amount of or on a hydrostatic pressure head, and is used a lot in the outdoor protective fabric industry. And I was mentioning a new type of performance for DWRs and water repellents is called stormproof, and this is the ability to be very resilient in a high rainstorm environment. So very good protection from sustained water impact. Also, a high level of hydrostatic pressure resistance for a fabric that's been treated but is not necessarily backed up with a film or a membrane. So having this ability to resist high impact rain and long duration rain and maintain dryness and fabric breathability is really what this new type of finish is promoting. Also, the ability to preserve these properties after laundering and multiple home launderings, and also having some repellency to oils and oily stains are all part of this new category that we're calling stormproof finish. And the Bundesman is the basic method for determining if a fabric finish would be in the storm-proof category. And again, the Bundesman is a rainstorm simulator where the water is dropped from 5 feet high and in a way that simulates a heavy rainstorm. And in this particular case, I'll show a Bundesman test where we have a same fabric treated with a typical DWR, which would give us like an 80-20 type of performance, and I'll show you what that means in a second. It's a fairly, a good level of resistance to light rain, and one that would give the storm-proof type of performance. So this Bundesman test, it rotates as the water is coming down on it. And you can see the standard wets out fairly quickly, even though it would pass the typical spray very easily and give a 100 spray rating. Again, you can see the wetting, the drops sticking to it. Now, the one with the storm-proof finish is completely dry and would remain so for quite a long period of time. This will go through a little bit of a time where that's after about a 5-minute duration, or actually it's about 10-minute duration. The control, or the 80-20 typical DWR, is wetting out considerably after about 10 minutes, and the one with the storm-proof finish remains completely dry. Now, some of the market applications for a storm-proof breathable finish include outdoor applications like awnings, boat tops, boat covers, even on a car as a convertible soft top finish or a car cover, indoor-outdoor upholstery, and probably the largest type of an application would be in outdoor apparel. The versatility and performance of a storm-proof breathable finish versus, say, a laminated structure is shown in this figure. The protection, as far as the repellency, is similar. I mean, it's the ability to completely prevent water from penetrating the typical fabric is shown there. It would perform very similarly to a laminated structure in many regards. The comfort level, now this comes down to the breathability and the ability to keep being breathable even after exposure to a high level of water impact. Recyclability, when you use a storm-proof finish on just a simple woven or even a knit fabric without a coating or a backing, make the material much more simple to recycle. It also provides a level of flexibility in the design of the garment. Just using finished fabric as opposed to a coated or laminated structure can give the designer more flexibility in making lighter weight, more comfortable garments. Also, responsible resource usage. Just finishing as opposed to finishing on top of multi-ply or multi-coated laminates could give you certainly savings in materials, energy, and then again the recyclability. The storm-proof breathable finishes give very high performance on synthetics like polyesters, nylons, and blends, as well as natural fibers. Gives a very unique combination of high hydrostatic pressure resistance for an unlaminated material, very high water impact resistance, and also resistance to other types of liquids like oils and stains. So the different, in the apparel industry particularly, the different types of weather protection options available are the durable water repellents, the DWRs, which I've been mentioning from the beginning. DWRs typically would make your jacket or a hoodie with beat up water in a light rain. A coated fabric is something that is used in rainwear quite a bit. It's for blocking water completely, and it would kind of act like house paint to protect your house, without allowing any water in. And then there are the membranes, which are semi-permeable films that are glued onto fabric to, again, give you more water blocking ability. So the DWR, durable water repellent, that stands for, and the materials I've been talking about, stormproof, fall into this category, although they are not really what you'd call a typical DWR. All DWRs are designed to apply in a mill and usually using the dip method, squeeze, dry, and cure. The industry spec is usually 100 initial spray on the A² 22 test, and then an 80 spray rating after 20 home laundering cycles. And that's not particularly hard to do, particularly on synthetics. It's a fairly easy spec to meet. Fabrics that are not backed up with anything, that are just a fabric treated with a DWR, are fine to run to your car in a light rain, but wouldn't really give you much protection if you're standing out in a heavy rain waiting for a bus. So they do give, typical DWRs give good protection against short periods of light rain. Now, DWR fabrics have been coated for many years, and then sometimes the coatings don't have a DWR, and they're just coated in order to give water blocking ability. And these are used and are still used quite a bit in rainwear. These are based on liquid coatings that are applied typically to the back of the fabric, and they're often based on polyurethanes. And so if there is a DWR on and the water gets past that in a high rain, then this blocks the water from getting to your skin. Typically, the 80-20 spec is used for this, and the DWR is really needed on the fabric to prevent weight gain and wet out, so the fabric doesn't become soaked and heavy. Again, a coating would go across the fibers, like a house paint goes across your shingles. The problem is when you're wearing a garment made from this is that it's difficult for the moisture that you generate, the sweat or perspiration, to get through that coating to the outside. So you basically become kind of sweat wet from the inside. So these are fine for if you're just running to your car quickly in a rain, and they're fine if you're just standing around waiting for a bus in the rain. But if you have to run after that bus for any length of time, they might become very uncomfortable from the inside. Yet some of the other problems that the coatings can impart are they can affect the hand feel of the fabric, and again the breathability limitations of the coating itself. It involves more complex processing. The end garment is more difficult to recycle, and again it would lead to a more complex supply chain for the manufacturer, opposed to just using a high-performance DWR. Membranes are more sophisticated systems where a semi-permeable film is glued onto the fabric, adhered to the fabric. These can be, the little diagram on the right, can be composed of many different layers for many different reasons, which I can't go into in the scope of this talk. They typically also will use a DWR in the face, and the spec is usually at 180-20. And this, again, is to prevent weight gain and the wet out of the fabric, which if the fabric becomes wetted out, the moisture from the inside, the perspiration, has a difficult time getting out across that. So you can become, again, sweat wet if that becomes wetted out too much. Some of the materials used include PTFE, which is Teflon, basically, polyurethanes, and combinations of different polymers. They're made to be semi-permeable, so they do breathe. They do move moisture, and and can move, air through them under certain circumstances, and they're glued onto the fabric itself. The coating, it's like a coating, so it does go across the fibers. So you lose whatever permeability you had from the fabric itself. Again, this would be fine to run to the car quickly in a storm, or wait for a bus for a while in a storm. But again, like the coated systems, if they wet out, it's uncomfortable for running after a bus. Membranes, again, are probably the most complex processing technology. Again, probably more expensive, most expensive of the three, more resource intensive. They can provide or cause some difficulty in recycling due to the multiple materials that make them up. They can have an effect on the feel of the fabric, and in so limit some of the design options available for athletic wear. So the stormproof finish, again, for apparels, provides very high water impact resistance. So we measure this in the Bundesman test as shown earlier. It's a very resilient, very high durability finish that retains its properties after multiple home launderings, and even more intensive launderings, like a killer wash that some brands use to rate different treatments. It also offers the ability or the possibility of manufacturing a membrane-free rain system that could pass the A² rain test, prevent the sweat-wet discomfort because you maintain the breathability, and give designers increased apparel design options. You might wonder, what is it about this particular stormproof finish that gives this type of behavior? And we believe that it's the ability of the chemistry involved to very uniformly envelop the fibers with a very uniform, adherent, and a well-organized, oriented coating. A standard DWR, while able to give the minimum amount of repellency required for most specs, would typically leave a more disorganized type coating, and one that's more easily lost by abrasion and laundering. So some of the sustainability advantage, which is becoming a more important feature in many apparel applications or among consumers and the brands that serve them. Just using a stormproof finish on a single ply fabric can give you much enhanced savings in energy, materials, and manufacturing time. By avoiding the different adhesives and films and coatings, the final product can be much more easily recycled. In summary, there are a variety of chemicals and chemistries available for making textiles repellent to water and oils. Most commercial repellents give a fairly low but a reliable level of repellency, and most repellency test methods are kind of geared towards that particular spec. Much higher repellency is available using advanced DWR chemistry, and this emerging DWR technology, which we call stormproof, can give a new class of performance for light, comfortable, rain-defeating apparel. I'd like to thank you very much for your attention. Happy to answer any questions.
Thank you, Frank. And just a reminder, if you have any questions, go ahead and submit them right now into the questions box. Right now we have one question, and it's, why aren't there abraders on the Bundesman?
Abraders? Oh, in that particular case, we weren't using them, but I didn't describe the full use of the Bundesman. And there, when it's run in its full capacity, there are abraders or devices underneath that kind of rub against the back of the fabric or the inside of the fabric to simulate a garment being on somebody and they're moving. And so sometimes we use those, and sometimes we don't, depending on what we're testing. But that does make the test, that would make a test more aggressive.
Okay, we have a couple more questions in now. It seems like this type of new innovation can be used in so many and various applications. Is this right?
Absolutely, yes. Yes, it's not just for apparel. It could be used in outdoor applications, and we have actually shown that in things like boat covers and awnings and so forth. It gives a very high level of repellency and enhanced hydrostatic resistance for an unlaminated structure.
Okay, great. Our next question, do you think that oil repellency treatments, no, sorry, they're coming in so fast now. Do you think oil repellency will ever be achieved without using fluoropolymers? Sorry about my pronunciation.
Oh, no, that's fine. It's going to be very, very difficult to do that strictly with chemistry. There may be some type of, a smart material that maybe you might be able to use some sort of outside mechanical, forces or something like that to do that. But it's from a chemical standpoint, I think it's going to be very difficult. We have certainly tried ourselves to come up with fluorine-free materials that give some level of oil repellency, and it's very, very difficult. And at present, it's not available. The fluorochemicals are, like I said, they're like nothing on Earth. They are, to get that level of low surface energy with anything other than fluorochemicals, it's hasn't been shown yet.
Okay, and our next question, how do you see water repellency treatments being applicable for leathers?
For leathers, it's a little more of, you can, I mean, it depends on the level that you need of repellency. It's more difficult to make a more of a planar surface repellent than it is of a more porous or sort of fuzzy surface like a fabric or a textile. Just having to do with the surface morphology that you need to create to get high repellency on a somewhat smooth surface like a leather. But you certainly can get a level of repellency. To get the kind of repellency we're describing here for the stormproof, it might be difficult, but it's not impossible.
Okay, and are you aware of any tests to differentiate between C6 and the C8 and other technologies that have leads to PFOs, et cetera?
Nothing that's really that simple in that you couldn't do without a pretty sophisticated chemical laboratory. I mean, I believe that there are certain chemical methods that could be used. The most foolproof is really extracting it and running it through like an LC mass spec, which again most people don't have access to get a true identification of those types of groups. So the answer is there's no real that I know of. There's really no simple way of determining the length of the fluorochemical chains.
Do storm-proof finishes affect the air permeability of fabric?
Typically, they do not. Again, with a chemical finish, like stormproof or even a DWR for that matter, they're leaving a very, very thin film on the fibers themselves. So the porosity of the textile itself usually is not affected. So, and that's basically where the breathability comes through, or the air permeability will come from.
Are these fluoropolymers compatible with cationic systems when formulated?
Yes, for the most part. The vast majority of fluorochemical DWR compounds are either cationic or non-ionic, and that both of them would be compatible with other cationic or non-ionic additives. They would not be compatible with anionic additives, which are, again, used quite a bit for other things in textile processing. So you have to be careful, what you put in the same bath, or you can have instability.
Okay, and what is the basic chemistry used to make the stormproof breathable finish?
It is a C6 based fluorochemical is the main actor in the finish. There are other additives that are used to improve the durability of the finish, and pretty much as we can really tell at this point or disclose.
Okay, and can this type of stormproof finish be applied to any type of single-ply fabric and still pass the rainwear test?
Well, there are more than several factors that kind of go into that test, and one of them is type of fabric. I mean, in order to design a rainwear garment based on single-ply fabric, it would have to be a fairly tightly woven structure, and so you can't use just any type of construction. We've, as far as the fiber composition, I mean, we've shown that the stormproof finish can even have a cotton-based material pass the rain test. So it works, it works very, very well on all synthetics. And it can even, given the right type of fabric construction, even pass on a very hydrophilic material like cotton. But if it's too open, if it's a very open knit or very open woven, then it may be difficult to pass that, because you will get enough pass through to fail that test. But it works on quite a few constructions.
Okay, after laundering, how does the water repellency hold up? How many launderings? What about hex bar abrasions?
What was the last part of that, please? Oh, what kind of abrasion?
Hex bar abrasions.
Hex bar?
So like those abrasion rods.
Oh, okay. We haven't really tested it against that. We certainly have tested it against the abrasion you would encounter in multiple home launderings. And for synthetics, polyester, nylon, the types of repellency that we showed in the Bundesman demonstration would maintain for at least 20 home launderings, and maybe more. It depends on the fabric. Polyester being the easiest one to get multiple, even beyond 20 home launderings, and that level of repellency, or high Bundesman repellency. For things like cotton, it'll be less. We certainly do it initially. After maybe 5 home laundries, you might be able to still get a very good Bundesman rating. But for things like nylons, polyesters, I mean, 20 plus is not hard to achieve.
Okay, and can stormproof be applied over other worn or washed off DWRs?
Well, I mean, theoretically it could be, but it's still applied typically in a mill setting. If you were washing it off, something like that, you would still need to go through a curing step. So whatever the fabric was that was cleaned off of whatever was on it before would still have to go through, an oven curing step to fix the coating onto, or fix the finish onto the fabric.
Do you produce the fluorochemical type repellents?
Yes, we do. The final product we do, yes.
Okay, and how long does the treatment last in terms of, oh, we already answered that. So how do fluoropolymers affect the flammability of fabrics?
They affect the flammability less than other types. For instance, they certainly, they're flammable. Again, because if they were completely like Teflon, there wouldn't be a problem. They'd have very high flammability resistance. But the majority of the finish molecule is really like an acrylic or a polyurethane or some backbone like that, and those will burn. They burn less than something that didn't have any fluorochemicals in them. But probably the best you can get is almost like a net zero effect on the flammability. For the most part, you would need some type of a flame retardant to be used if you're expecting, the fabric to have any kind of flammability resistance.
Okay, and what are the application techniques you can use for this stormproof technology?
As I mentioned earlier, it's designed to be applied in a mill setting. Again, the most common high volume method is preparing a bath and dipping the fabric roll to roll through the bath through pads that squeeze the excess out, and then it goes through a curing oven. Like really any type of DWR, it can be foamed and applied to one side, and again, having to go through an oven curing step. It could also be applied by the exhaust method, where a garment or a roll of filament, for instance, could be put in, and the DWR comes out of the solution and onto the surface, and then that is taken out, kind of dewatered, often by almost like in a dryer type application, and then cure it onto the fibers. You can't spray it and have it go on at room temperature or anything like that. In fact, we'd never recommend any type of fluorochemical be sprayed because it's probably not because of for health and safety reasons. You shouldn't really spray apply these types of finishes.
How is your non-fluorinated product different from others on the market?
Yeah, I didn't really get into that, but ours, it's basically the way we find the performance of it is the durability. Our fluorine-free, which is called F3, is very, very durable, particularly on cotton materials. So it really differentiates itself. It works very, very well on synthetics, polyester particularly, but where it really sets itself apart is in blends with cotton and natural fibers themselves. The durability to laundering is much better than other non-fluorinated products on the market.
Okay, and we have time for a couple more questions. Are there stormproof fabrics available which are food safe?
We don't do that type of testing, So I'm not really sure if a particular manufacturer of the fabric themselves have done that. So I don't know. I would probably say I don't think so, but I don't know for sure.
Okay, and what are the most important processing factors when applying DWRs?
Oh, that's a great question. One of the most important factors is the cleanliness of the fabric that's being treated. You definitely want the fabric to be cleaned of other processing chemicals, particularly things like silicones, surfactants, things like that can alter the effectiveness of the DWR treatment. The amount of the concentrate, we basically sell, and other manufacturers sell concentrates of the DWR, which the mill would dilute with water and apply. And then how much of that bath liquor gets transferred to the fabric after the squeezing, we call that a wet pickup. And how much, so we really want to know how much of our DWR concentrate gets onto the fabric. So that's very important. You need to be able to know that you're getting enough on to get an effective finish. And then, of course, the drying and the curing conditions are very important. You don't want to undercure. You really don't want to overcure the finish on there. But undercuring is the worst part. If you don't get enough heat and duration of the cure, you won't get the same type of repellency properties.
Okay, and we are just about out of time. Thank you everyone for your questions. If your question was not answered, you can reach out to Frank. His information is on the screen. And please feel free to reach out to ATP staff for more information on the division membership and its programming throughout the year. Again, a PDF and recording of today's content will be emailed to you. Thanks again to Frank, and thank you all for attending.
Thank you very much.